Is it possible to track blood pressure continuously without the discomfort of an inflatable cuff, simply by listening to the heart? The researchers behind this work investigate a novel method to do exactly that using acoustic signals. Standard blood pressure measurement relies on inflatable cuffs, which are bulky and inconvenient for long-term use. This limitation makes it difficult to track potentially dangerous fluctuations caused by mental physical stress throughout the day. To solve this, the authors utilize pulse transit time, or PTT. This is the time it takes for a pressure wave to travel from the heart to a distal point, like the finger. As blood pressure rises, arterial walls stiffen, causing the wave to travel faster. Most prior research calculates timing using ECG signals, but that introduces an electromechanical delay, known as the pre-ejection period, which can skew results. This study instead uses the phonocardiogram, or PCG, to detect the S1 heart sound, marking the exact physical moment blood leaves the heart. Let's examine how the researchers operationalized this acoustic approach into a working system. The core method involves defining a precise time interval. The start is marked by the peak of the S1 sound from a chest microphone, and the end is identified by specific features on a photoplethysmogram, or PPG, measured at the finger. To translate this timing into blood pressure, they employ a linear regression model based on the inverse of the PTT. Because arterial properties differ from person to person, the system requires an initial subject-specific calibration. For the hardware, the team combined a simple electret microphone on a chest belt with a green optical finger sensor. Crucially, they placed a force-sensing resistor under the reference cuff to perfectly synchronize the ground truth measurements with their signals. With the system built, the authors tested its accuracy against standard cuff-based monitors. They evaluated the system on 24 healthy adults who ran to elevate their blood pressure before recording. The results showed strong correlations for both systolic and diastolic pressure, with error rates comparable to more complex ECG-based methods. The significance lies in the simplicity. By replacing electrical leads with a microphone, the system eliminates the need for skin electrodes. This low-cost architecture opens the door for integration into smartphones and other portable health devices. To learn more, head to emergentmind.com.